a body in simple harmonic motion has got two types of energies. One is potential energy and another is kinetic energy. The potential energy of the body is by virtue of its position with respect to the mean position, and the kinetic energy of the body is by virtue of its velocity. As we have discussed earlier the various topics of simple harmonic motion, we know that displacement equation is given by y is equal to a sine of omega t if a body is executing its simple harmonic motion from its mean position. The velocity as given by differentiation of this displacement with respect to time, that is given by a omega cos of omega t, and acceleration is given by differentiation of the velocity with respect to time, and that is equal to a omega square sine of omega t. Now we can also see that a is equal to minus this a sine omega t is equal to y, so acceleration is equal to minus omega square y. Now, as already told, the total energy in SHM is sum total of potential energy and kinetic energy. The potential energy is by virtue of its position with respect to the mean position, and the kinetic energy is by virtue of its velocity. Now we will see how to calculate the kinetic and the potential energies. We see that when a body is disturbed from its mean position, there is a restoring force that always tries or brings this body back to the mean position. Now, when a force is displacing a body from its mean position, it is working against that restoring force. So that work done against that restoring force is stored in that body or in that oscillator as its potential energy. Let us go into the details. The restoring force F is equal to mass into acceleration, as acceleration calculated already is equal to m minus omega square y. So F is equal to minus m omega square y. This m omega square is equal to k, that is force constant. So F is equal to minus k y. Now this is a restoring force, so when a body is disturbed from its mean position, the work is done against this restoring force. Let us now say that for a small displacement dy, a small amount of work dw is to be done. So dw is equal to minus f dy. Why minus? Because that work is to be done against that restoring force. Now calculating, dw is equal to minus, as F already calculated, minus ky dy. So dy is equal to ky dy. Now this is a small amount of work dy. If we have to calculate the total amount of work done in displacing a body from 0 to y, for a displacement of y units, what is the total amount of work? That total amount of work remains stored in the body as its potential energy. So we calculate that potential energy is equal to integral of dw from 0 to y. That is integral of ky dy from 0 to y. So u is equal to k being constant is got out from the integral sign, and y raised power n integration is equal to y raised power n plus 1 divided by n plus 1. That is y 1 plus 1 divided by 1 plus 1. That is equal to 1 by 2 ky square. So potential energy is given by u is equal to 1 by 2 ky square. Going for the kinetic energy, we know that kinetic energy is equal to 1 by 2 mv square. In the case of simple harmonic motion, v is equal to a omega cos of omega t. So kinetic energy is equal to 1 by 2 m a omega cos omega t whole square. So k is equal to 1 by 2 m a square omega square cos square omega t. Now K is equal to 1 by 2 m omega square A square cos square omega t. This m omega square is force constant, that is K. So kinetic energy is equal to 1 by 2 K A square cos square omega t. This is one expression of kinetic energy. Now we know that cos square omega t is 1 minus sin square omega t. So written as K is equal to 1 by 2 K A square into 1 minus sin square omega t. Now y is equal to A sin omega t. So sin omega t can be written as y divided by A, and sin square omega t can be written as y square by A square. Putting this relation y square by A square in place of sin square omega t, we get kinetic energy is equal to 1 by 2 K A square into 1 minus y square by A square. Cross multiplying it, kinetic energy is equal to 1 by 2 K A square into A square minus y square divided by A square and A square is gone. Now kinetic energy will be equal to 1 by 2 K A square minus y square. This is the relation for the kinetic energy. Now the total energy is sum total of kinetic energy and potential energy. So we get total energy E is equal to U plus K. E is equal to U, as already calculated, it is 1 by 2 K Y square. Kinetic energy is equal to 1 by 2 K A square minus Y square. Simplifying it, total energy is equal to 1 by 2 K Y square plus 1 by 2 K A square minus 1 by 2 K Y square. This 1 by 2 K Y square and 1 by 2 K Y square is gone. So E is equal to total energy is equal to 1 by 2 K A square, where K is the force constant and A is the amplitude of the vibrations. Going into the details now, at mean position or T is equal to 0. Now displacement at mean position is equal to 0. So kinetic energy is equal to 1 by 2 K A square minus 0 square, that is 1 by 2 K A square, and potential energy is equal to 1 by 2 K Y square. As Y is equal to 0, potential energy is equal to 0. So the total energy is equal to 1 by 2 K A square. That tells us at mean position the whole energy, the total energy of body is in the form of kinetic energy and the potential energy is 0. Let us see at extreme position. At extreme position, or we can say that at T is equal to T divided by 4, where T is the time period of the oscillations. At extreme position, Y is equal to A. The displacement is equal to the amplitude of the vibrations or oscillations. So potential energy is equal to 1 by 2 K A square. Now kinetic energy is equal to 1 by 2 K A square minus Y square. But here Y is equal to A, so kinetic energy is equal to 1 by 2 K A square minus A square, so kinetic energy is equal to 0. So sum total of energy is equal to 1 by 2 K A square. So at the extreme position of the oscillations or extreme position of the vibrations, the total energy is in the form of potential energy, that is 1 by 2 K A square. The kinetic energy is equal to 0. That should tell us why that body doesn't go beyond that extreme position, because at that extreme position the kinetic energy of the body is equal to 0. Now seeing the variation of potential and kinetic energy with time, we can plot a graph is plotted like this. Now we see that the dotted curve shows us the variation of the potential energy, and the solid curve, black curve, shows us the variation of the kinetic energy. We can see that at time is equal to 0 or at mean position, the total energy of the SHM is equal to the kinetic energy. Now, while going from mean to extreme position, the kinetic energy decreases, and at extreme position, the kinetic energy is equal to 0. Now, going from T by 4 to T by 2, that is from extreme position to mean position, the kinetic energy increases and becomes maximum at the mean position. Now, again, at 3T by 4, the body from T by 2 to 3T by 4, the body goes from mean to extreme position. That means the value of the kinetic energy again decreases to 0. When coming back from extreme to mean position, the kinetic energy increases from 0 to the maximum value. Now, seeing the potential energy at mean position, as the displacement is equal to 0, the potential energy is equal to 0. When the body goes from mean to extreme position, as the displacement increases, the potential energy increases. So, potential energy increases from 0 to maximum value, because at extreme position, the value of the displacement is maximum. Now, when the body goes from extreme position to mean position, that is from T by 4 to T by 2, the potential energy as well as the displacement decreases from maximum value to 0 value. So, the value of the potential energy decreases from maximum value to 0 value, and the cycle repeats. We see that here an important thing to note is from 0 to 4T by 4, the simple harmonic motion completes one full cycle, but the variation of the kinetic energy and the potential energy completes 2 cycles. So we see that the frequency of the change in kinetic energy and potential energy is twice the frequency of the simple harmonic motion. The variation of the potential energy and kinetic energy can also be seen by help of this graph. We can see that we have got 2 lines. One is a dotted line and another is a solid curve. The solid curve shows the variation of the kinetic energy, and the dotted curve shows the variation of the potential energy. Now we see that at the mean position, at the 0 position, the potential energy of the body or the potential energy of the oscillator is equal to 0, and the total energy is equal to the kinetic energy. So at the mean position, the total energy of the oscillating body is in the form of kinetic energy. At extreme positions, whether it be in the right extreme or left extreme, the total energy of the body is in the form of potential energy, as at the extreme positions, the kinetic energy of the body is equal to 0. So, at minus A and A, the solid curve which shows the variation of the kinetic energy, the solid curve, the value of the solid curve is equal to 0, and the value of the dotted curve is equal to maximum. At mean position, the value of the dotted curve is equal to 0, and the value of the solid curve, that is kinetic energy, is equal to the maximum. So we can see that at the mean position, the total energy is in the form of kinetic energy, and at the extreme position, the total energy is in the form of potential energy. Thank you.